we're going to go through construction, planning, and demonstration. How to build using the technology that I'm going to show you, so the construction part. How to plan to be able to get some of the projects that Samuel showed you. What was the thinking behind it from an architecture and planning perspective. And then some demonstrations. Since we did what we did, what happened? And what did we learn? And how can those learnings from the project be shared from SCAT to all of you in their final phase, which is a phasing out and skills transfer phase. So CPD today, or at least for my little time with you, is construction, planning, and demonstration. So let us start. First module, construction. So we'll start with my disclaimer. And the disclaimer is all building materials are interesting. All building materials have their value, whether they be AAC or volcanic rock or stone or light gauge steel. This is a bad rukarakara, but all of those things have value. As Samuel explained, however, what the task is of the ProEco project, of the Swiss Embassy and SCAT, is to really understand which ones are suitable for what in our context. So all of these materials have value, but today we're specifically going to focus on brick, as Samuel told you, because brick has, there's a lot of clay here in the region, and that clay is of great quality, and so why not use it to create local jobs and build materials? One of the other things that, and I'll start just briefly with this, one of the other things that SCAT and the ProEco project does is monitor the price of materials. And I know you actually can't read this, and I don't mind that in this case, is because these are all building materials that they monitor on a monthly basis to really understand the cost and the fluctuations that are happening. And so what I'm showing you here is a screenshot from before our pandemic, right, in January 2020, and all the way up to October 2021. And what we can see is, of course, during the pandemic, which hit in April, a lot of the borders shut down, so a lot of materials were not able to come in. But what that also meant is that things really haven't stabilized since. So if green is the least expensive, yellow is a little bit more expensive, and red is the highest price, you can see that we're having an issue here in terms of price, right? All of you who are building and designing projects, you know that you have to start to control your quantities if you actually want to be able to address and deliver the affordable housing that's being asked of from all of us here. And so this really is the backbone of what SCAT and the project are trying to do, is to figure out how to develop solutions, design solutions that can exist within this context and still deliver at the price point that we need. SCAT started to look at different walling materials. And this is the one we're going to talk about today, is the rolock bond, the RCC reinforced rolock bond wall. And it really is a function of looking at all the walls, looking at all the building material inputs, seeing that, you know, this one relies on a lot of cement and plaster. We saw the prices of cement go up quite a bit during this last period, and it continues to rise. Traditional bricks also requires quite a bit of cement mortar and concrete for columns, etc. So looking at this type of study and trying to understand how to make the best use of some technologies that might be able to optimize our building material usage here. And so SCAT came up with the idea with using this. Now, this is the rolock bond, and if anybody knows it and sees it, you'll see that there's a unique pattern that's this cross pattern. So as you're driving around town, the minute you see this cross, you know you've seen a rolock bond. And what that means also is that you're seeing a cavity wall. And that cavity wall has a lot of potential thermally, but also structurally. And that's what we're going to talk about today. So the rolock bond is nothing that the Swiss or SCAT or invented. The rolock bond has been around for a long time, specifically even before the Industrial Revolution. So this house here is from 1801. We can see our cross there, and we know that this is a cavity wall system. And so again, 1856 in Canada, we're seeing this rolock bond pattern. And the reason why it was first invented was for workers' housing in the Industrial Revolution. And so being able to have a wall that is cheaper, that uses building materials or minimizes the use of building materials is something that they were interested in even back then. And so it's particularly appropriate to us now, where we're having issues of high cost of materials, and yet were expected to deliver the affordable housing between 10 and 35 million. So the rolock bond, actually, even the Americans got in on the action in the 1950s. And this is a rolock bond that's 9 stories tall, which means it is a technology that is able to be adapted to different situations and different structural, you can adapt the structural system to be able to do different kinds of buildings. And this was also a low-cost housing building. Another one built in Nepal, similar thing, and this one was actually built by SCAT in Nepal, really trying to optimize the floor plan, optimize the interior circulation to do something extremely basic that can deliver at the right cost and making good use of materials. Now this is particularly interesting in Nepal because if anybody knows Nepal, they know that there are some earthquakes there. And this is also a high seismic region. So again, all of a sudden there's a parallel to think about why this is interesting for that context and why can it be interesting for ours. Again, what can you do structurally to this wall that you can't do to others that could help you respond to these issues of future shaping? You can do fancy stuff with rolock bond. You can do curvy stuff with rolock bond. And SCAT did boxy stuff with rolock bond. And the boxy stuff has a reason. That boxy stuff is because that's how you can make sure that this is structurally sound. The first time I ever discussed this building in public, someone stood up and said, "You are being incredibly irresponsible, Fatu. Showing us a building with no columns, how dare you?" And I realized I forgot the slide that showed him all the internal structure. So today we're going to talk about all the internal structure, okay? So that I don't get that comment again, and you know that SCAT is doing good and responsible work by putting up buildings that are structurally sound. Just to do a quick recap, here are our different walling systems. This is the one we're interested in. We're interested in it because it really minimizes our material inputs. This is kind of significant here, especially if our bag of cement has gone from 9,000 to 13,500 recently. Thinking like this becomes quite important. So even if you don't like the designs of SCAT, that's fine. It's not about the design, it's about the structural system that's being proposed, and then all of you architects should be able to take the structural system and make it beautiful and all of the other things that SCAT as a project does not need to do. Again, just reminding you, here are the prices of materials and the way that they're jumping. Here is cement also jumping during these sensitive times, so we need different solutions. Within these buildings, these rolock bond buildings, secretly, and this is one that you'll visit if you go on the tour tomorrow, there's all this business inside. All of this is making sure that this building stands straight, that it resists seismic forces, and that it also can be a system that can allow a maximum number of people to live in there comfortably and at a good price. What's actually inside? So let's take a peek. So you've got your cavity wall here, and you essentially have 3 basic details. You can do rolock bond. If you master these details, this system is for you and easily deployable. So we're gonna have some vertical reinforcement. And that vertical reinforcement, what it's doing is exploiting the cavity and using the brick S formwork to actually pour a mini column, shall we say. But it's not so much a mini column as a stiffener, we shall call it. And when it's placed around a corner, it replaces your traditional column, right? So a column would be if I'm standing on 1 foot. But this, which is then tied around the corner, is almost like a truss around the corner, and it's actually more resistant. And that's how my seismic or my shear forces and my lateral forces that specifically at the base of the building are getting the most push and pull, that's actually how that's resisting. Then if I have a particularly long wall, I'll put a couple more of these vertical reinforcements. And if I have a T, I can then put these 3 and I will tie together. And again, all the reinforcement details for this are available to you through SCAT and the project. And so please feel free to go ask if you want to see any of this. And so this vertical reinforcement is going from the building. It's tied into the ring beam and goes straight up. Then the second type of reinforcement is horizontal reinforcement. About every 1.20 meters, almost a corset, right? Which holds and cinches the building together. And again, between the 2 systems, so you're gonna have your vertical, which I just showed you here, and then your horizontal reinforcement, which goes and ties the building together and also allows you to tie together these corner details. So all of a sudden you start to have this grid inside of the wall that is basically using the wall as formwork, but the wall is actually load bearing. So we're moving away from a typical column beam structure, right? Where all of your loads are point loads that are transferred to your beams and coming down to the ground to footings. No, in this situation, the wall is the load bearing wall, which is why the quality of the brick matters so much, which is like why people like Samuel, who presented, who is a mechanical engineer, but specialized in brick making, that he is so important, because we need a brick here that has at least 10 megapascals to be able to resist those loads. Okay? So the wall's load bearing, it's bringing the loads from top to down, and then inside, to resist all the shear forces, are these tricky little reinforcement. Well, actually not tricky, sly reinforcement that fits into the wall. So again, you end up with this cage. Here's an example of these corner ties that every 60 centimeters, so every 60 rows of bricks, you will tie your corners. Here's your T reinforcement. Again, and one of the things that SCAT offers is training to masons and technicians about how to design these details. Again, for you architects, no problem. It's very simple, but to make sure that your masons and inspectors execute it and supervise it correctly on site. So again, here is an example of our reinforcement and then the ties that come. Everything here has been pre-calculated for you, pre-engineered for a building that goes up to G+2. Anything beyond that, we'll talk. But G+2, you're good. So since the walls, as I mentioned, are load bearing, what it means is that the forces are being, or the loads, dead and live loads, are being carried down these walls, and anything you do here in the front or in the back is fair game. So design-wise, I could have a bay window. I could have just a curtain if I wanted to leave everything open. I could have a big commercial storefront. I could have a small door. Anything you want to do on this side, because it's not carrying the majority of the loads, right? So really, it's these side long walls. So instead of I don't know if you know, we had called this house the Swiss cube, but it's really a Swiss tunnel. Okay, so these are the walls that you can make as long as you want and then do anything within this opening. Rolock bond is very well adapted to this. If you want to do something fancier, that's fine. Then you would start to do a calculation to see whether or not it's the right technology for you. But for something simple and durable, and possibly to assist in the densification that is being asked of us as architects working here in Kigali, this also might be of interest to you. What this means then is, because these are my load-bearing walls, I'm going to have my slabs obviously be carried on those walls. So I would put my slab system this way. Then when I start to design, it makes most sense, if I'm going to have stairs in a storied building, is to remove a portion, to remove one of the beams here, one of the floor joists, and have the stair go that way. Again, the objective is to do something that minimizes material consumption. It may not be beautiful, but it has to be smart. That's what we're looking for right now to tackle this affordable housing challenge, is smart use of materials and construction technologies. Also, what this means, which all of you, of course, will understand, is if you have this load-bearing wall, the first thing you want to do is not cut a big hole in that wall. Otherwise, you'll start to have to reinforce the lintel here, and then you lose all of the advantages of having this front being able to be completely open. So again, when you visit the SCAT houses tomorrow, or the Proeco houses, excuse me, just know that this is the logic of trying to optimize the materials and the construction techniques that we have available to, again, come up with the best cost house as possible. Which is why, if those of you who have visited PSF, you've seen the 8 million house, and it says 8 million on it because it cost 8,185,000 francs in 2017, August 28th, when we inaugurated it. And so what it means then is, if these walls can be as long as I want them to be, and I'm going to carry and they're going to carry the load of my slab, the only constraint that I have so far is my slab system. okay? And so when you start to think about MaxPan, those of you who have used Rulibuz's beautiful MaxPan product, you know that there's a MaxPan of 12 and a MaxPan of 16, and those depend, the depth of those MaxPan depend again on the span. Same if you wanted to use a timber floor system for this. It's going to be about the available timber that you can get. 400 meters, that's readily available. 440, you can find it, but you have to chase it. So again, those are design decisions that you're going to make. Those are constraints that you need to understand of the system in order to make best use of it. In any case, so here's the timber floor solution, and you can see what's really nice is that it actually fits right into the rolock bond pattern. This repetitive cross pattern that we have, that bond, you can, this short one here is the rolock. This is the shiner. You essentially cut the shiner and you can put your wood joist right in there. And it's quite beautiful. You put your T&Gs on there, you can varnish, you can paint. The difference between eucalyptus and pine, one is usually not really well dried, which means you might have some warping, and the other one, sometimes it's soft, so you don't want to wear your stilettos into the bedroom after a rockin' Saturday night. So you see here, the system immediately can slot right into the rolock bond, 57 centimeters on center, and boom, 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 go right along the building. So that's the fourth thing you have to remember. I told you that there were 3 key architectural details that you have to remember about the reinforcement. The second one is where your slab system or where your beams, how they connect into your load-bearing wall. Once you recall that, you can essentially just plug and play all throughout a building or a series of buildings. Looks like this here in cross-section. You, of course, need to remember that wood likes to keep behaving, especially if it's a little moist. So you want to make sure that you wrap it before you put it in the wall. But construction-wise, this is very interesting because I basically don't have to stop, right? I don't have to waste time waiting for my slab to cure or anything like that. I put the joists in and the mason can continue building the wall, which means that in terms of speed, this also is quite an interesting system. So MaxPan, we did MaxPan, or SCAT did MaxPan in 2 ways. One with a precast beam system. So by using formwork and casting directly on site, after 7 days, you can actually take it out of the formwork, put the beam in place, put down your MaxPan, continue building, and then of course do your floor. That is not the way it is when you do in situ, is you'll have to wait 3, if not 4 weeks to have a floor that's completely cured. Again, these MaxPans, what you're all familiar with, I won't waste time there. These precast beams, also from SCAT and the project, the Pareko project, you can have access to this formwork. The drawings and things about how to detail this properly to fit into the wall, all that is available through the project. You can either do the in situ version or the cast in place version. And SCAT recorded the cost and benefits of each one to be able to share that with the private sector. But what it means then, once you do use a precast beam, you can of course plaster and make it beautiful. No one would know the difference. The main gain is in terms of time and the timber used or that you don't use for all the scaffolding. The MaxPan, again, this is that precast beam, can fit directly into the rolock bond system, which is incredibly useful. Again, 57 on center, you can start to pop, and put your MaxPans directly in there. So speed really is of the essence. And again, there aren't very many details to master, which means on site, you should be able to inspect this. You should be able to roll it out at a good pace if you're well organized and your materials are available. I can go into this later, but essentially in one of those horizontal, we'll call them ring beams, but one of those internal reinforcement that goes all the way around, you can actually put weighting bars. And so these 2 rebars that are coming up, and then this beam can hook onto those, can hook directly on to those bars, and then when you pour the screed, when you pour your 4 centimeters over your MaxPan, you then seal that whole system together. So you seal the wall and the floor, and then of course you get a really good tight bond. The fantastic thing about this is you're able to, with the same wall, put different systems. So if I want to have MaxPan on one side, I can have MaxPan then notching into the other side of the cavity. Or I can have timber on one side, MaxPan on the other side. You really can begin to vary. So here, a photo of the precast concrete beam on one side, and then you see the wood wrapped in plastic coming on the other side. Same detail that you see here. And then you pour all that together, really tying your building. So all of this because of this cavity wall and this module that really is quite flexible and user-friendly. The other thing that the cavity can be used for, of course, is to be able to run your cable channels, which is fantastic. So no longer do you have, in rooms that you don't plan on plastering, you don't have these channel covers or cable covers outside of the wall. You can start all the way. When you start from the base, you should put in those cable channels and then essentially continue up all the way. What this does is, since it really is a series of basic connections, the slab to wall connection, and then the few connections that are around the different corners of the building that allow you to deploy the rolock bond, which means that in this direction, you can stretch as long as you want. The width, you can stretch up to the tolerance of your different slab systems. You can also split the building, so you have one floor on the bottom, one floor on top. The reason that we explored going up is because if cement and roofing materials are our most expensive materials on the market, it becomes a lot cheaper to go up, to get skinny and go up, rather than have a landed building. So storied building is actually, in this context, one of the more efficient ways to build. The same thing is that you can start to use this system of stacking these volumes on top of one another, again, using the same system and using different types of floors to divide them. You can start to use the slope to your advantage, meaning I could have one entrance on the bottom and another entrance on the top. And then, of course, then my slope looks like this, so I don't do massive cut and fill, as we've seen many other places. I can actually begin to step down the hill lightly, which is cheaper and safer, and then notch my buildings around it. So the point is, essentially, is I can multiply my little Swiss cube box at the end. I can stack them on top of one another, and then I can assemble them into a creative building. And so we started with these cubes, which, again, everybody said, well, I don't want to live in a cube. And many people who came to the expo said, can I have a second window here? This, again, was all for demonstration to show that you can do one very, very easily and control your costs. So then if I skip quickly to the planning module, the P of our CPD, the question is, what thinking do I have to do to take it larger scale and to start to actually look at the city? On the left is the Kimisagara neighborhood, or Gitega actually, and on the right is a picture of the master plan. This is the new master plan, and they want us to build. They want us to get from here to here, okay? And they said that that's our responsibility, and we're supposed to do it between 10 and 35 million, so everybody can have access to a house. And actually, when I did a quick little survey to see in R2 and in R3 zones, which are the zones designated for upgrading, and looked at all the plots in Kigali, there are 40,000 plots that don't meet, not even in terms of size, the typologies that are being proposed, okay? And this is our problem, you guys, as architects. We have to come up with a solution to make sure that these people have appropriate housing solutions to be able to grow this city, meet the master plan. We all need to stay employed and have people buy houses, so we've got to be able to deliver them at the right price point. And so what it means is that somehow we need to get from this current situation to this, which is what the master plan is looking at. And our rolock bond cube system, which seemed pretty banal, can actually maybe help us get from 0 to 5, right? Because I know I can stack it. I know I can multiply it. I know I have very few details that I need to master. How can I mix that to be able to get what they're asking me for in the master plan? So as any good architect, we start with dreaming, right? And so we drew this comic strip, which I love this picture of Kigali. It's stormy, someone's house falls down, etc. She gets together with someone from city planning who says, why don't you merge your plots and make a new building? So we drew this, and said, okay, we're going to upgrade an informal neighborhood. This is what this could possibly look like. And so, like any good architect, you have a dream, so why not build it? So we built it. And the idea was to use, again, that same system of that cube, of those reinforcements in the corner, except for this tower is a little different. That's for another CPD day. But how can we begin to stack and get all the cost efficiencies using the system that we know, which is a cavity wall with some reinforcement in it? And so after we built that, we were satisfied for about 2 minutes. And you see right here, there was a beautiful panoramic window, which I hope you can see yesterday. We sat there, and then that allowed us to look across and say, oh man, we have all this to do. Okay, so that's where the second part of the project is to figure out how to scale up. We did, the first test was done using the technology, but again, as architects, how do we take that technology and turn it into something like this, which Samuel showed you and which you'll visit tomorrow. So we go back to our cartoon, which is where we get all of our inspiration, and realize that, okay, it's about meeting with the people, doing it through a participatory process, and figuring out how everybody can get at least what they had before, but better, okay? And so the team from SCAT sat with people and discussed, this is your option, you can have this cube, this cube, this cube, this cube, and the people are able to agree. This is the situation we have now. If we start to densify that situation, oh my gosh, we have a whole bunch of free land. Can that land be sold to be able to finance what's happening in the middle? So I could possibly have some commercial here, and then it becomes a planning exercise. We as architects really are responsible for thinking about how our construction systems actually have a reality and a vision and a language and a logic at the scale of the city. And so we take our plot, I'm hurrying up. This is where, you know, we might need some fire access when you're doing a new neighborhood. This is the old building here project. And then this was the whole big zone. And so what happens is if you start to take this zone and think about how to apply our cube system to it, we can maybe have some commercial down here, some residential down here where all of the people are currently living. So again, stacking and using this seismically high performance technology to be able to redo this neighborhood. And so this is what SCAT is now with the funding from the Swiss and the city of Kigali, mostly the city of Kigali for this part, are figuring out how to redevelop and build this using the system. So you'll see all that tomorrow. But again, the system allows, and this is a Rubik's Cube for those of you who play, the system allows you to break down what all the people had. So this is the existing plot configuration. Who had what, who had rental units, who had a store, who had et cetera. To figure out all their previous or existing, yes, I guess their existing situation. And then how do we start to, again, using the rules of the technology. So I know my slab can be this wide. I know my wall can go this tall. All those properties, all those structural properties, how can we begin to take everybody's choices and put them together into one building? And it's possible. And again, that's where we go back to our technology. Remember, we have our slab system that allows us to do max pan on one side, which of course is acoustically, it makes an acoustic divider, so I can have that when I'm have different buildings next to one another. And then I also, on the other side, could have my timber, which is cheaper, but maybe within the same house, acoustics aren't such a problem, so I can actually use this technology. So the whole time that SCAT was trying to negotiate this, they're also negotiating the technology and what the technology can do. And if there's anything that you take away from today besides 4 details and a load-bearing wall, it's that it's how you apply these construction and architectural systems that will really help you figure out what you need to do at a larger scale. And so now they have this. Congrats. SCAT, Proeco, inaugurated today. You'll go visit it tomorrow. Good job, guys. So 5 years from a catalog of ideas to this building and the other building, I think that's not bad. The second thing is that Proeco is also working in, and SCAT is also working in Bukavu. So again, a similar context of needing to be upgraded, small shops, people need to preserve this. This is how they make money. The real house is in the back. How do you use this logic to actually think about how do I put my Swiss tunnel in this situation, calculate it so that the income generation of these homes is the same as it was before, but the system gets placed into a context that maybe sometimes is a little challenging. In Bukavu, where land is incredibly expensive, made a smaller floor plate and then went taller. So this is 3 stories. And instead of having a garden outside like they do here in Rwanda, this was possibly, I think one of our proudest moments was the rooftop terrace that allowed you to see all of Bukavu. So all of a sudden you can start to think, even in this really basic system, how to take green spaces and all those other things that architects love and want to make sure that we have a place for in a crowded, busy city with high land prices, and actually think about how to put that on the top of your home. So, and I will end on a demonstration, the D. So showing you this was what the project was able to do using this technology, which is these 3 things, and then the big ones you'll hopefully visit tomorrow. But since the technology was first introduced, and since that house at PSF was put there on August 28th, 2017, all of these projects have multiplied across the region, and this is even a year old. There are over 2,000 copycat units using this technology throughout the city, and it's quite fun to drive around and take a picture. Once you see that cross in the bond, you know that that's the rolock bond. Ruliba now makes it, everybody's using it. Some of the IDP model villages are using it because it is an efficient way to use to minimize the consumption of expensive materials. This is an example also, just to let you know, done with white bricks, which are absolutely beautiful. This is in Kachiro. It's this one has a slightly different structural system, which, as I say, is a little bit more complicated, but we can go through another time. This is what the house looks like. Again, stacking up the hill. Interiors, beautiful. This is the interior in Bukavu. This is in Kanombe. Still the same basic rolock bond system that SCAT was using, but you can actually start to decorate it. That front facade that I told you that was flexible, this is what happens when, as an architect, you take a position about what that opening should be like. And again, the same system of the load-bearing walls on the side, et cetera, and has a totally different look. Another version, which is actually quite interesting, and I will end on this one, because this was actually a copycat of one of the buildings that we did. And that really allowed us to do a comparison with cost. The tests, the test that SCAT was doing in terms of should you pour in situ, should you do precast max pan, should you plaster, should you not. Since they did 8 units here, and we did 8 units at the other project, it really allowed us to see what the difference is in cost. And luckily, the owner of this building has shared all the costs with us so that we can actually do that proof of concept. And so we'll compare this building, which was our first 8, with theirs. And so when you make a choice of putting no plaster and no tiles in the kitchen or a bathroom, what is actually the difference? The tile used we had no tile in this building. The tile used for these 8 units was 14.4 million. And that 14.4 million was 21.4% of all the building material costs. So again, the decisions we make are important, all right? So this is totally appropriate, and this is for some markets and some contexts, but just understand that there was a reason why this was thought that way, and what the difference actually makes. And as a designer, you know, you make decisions. When do you introduce this? When do you not? And I think you can do both things in one building. Again, the cost in the SCAT building that you will see tomorrow, mostly it's triplex dividers, which people were very upset about for privacy. These walls in here are plastered. And again, the difference in material in plaster, the budget for these 8 units was 16 million on plaster alone for interior. So I've got my tile at 14.4 million. I've got 16 million now for my plaster. That's 30 million divided over 8 units. You do the math. We're talking about 4 or 5 million. And the city and the government and the ministerial instructions are telling us to stay between 10 and 35 million. So a dumb wall with 3 details and no plaster is starting to maybe have its place somewhere in the housing market. Not saying at all it should be the only thing there, but technologies do matter, and how you deploy those technologies as architects is an architectural statement, but also a statement about the context that we're living in, the clients that we're serving, et cetera. I'm almost done these, don't worry. The other thing that there was a big difference is that they poured all of their max pans in situ, and the cost of timber was a significant amount of their budget. It was over 20% of their budget was just buying the timber to hold up the floor during the pour. Some of that can be recycled and used for the hidden roof structure, but still, it was a large amount of money. So again, all of those choices about how you make things, as well as what you make, really have an impact on what we're doing.